Hello everyone, welcome back to the channel. In this video, we are going to discuss a GATE 2025 linear algebra problem and its complete solution. After that, we will see the core concepts involved behind the above problem. And finally, we will solve a few practice problems plus some problems for you to try yourself. So, let's begin. So the problem is an n-cross-n matrix A with real entries satisfy the property that is norm of ax square is equal to norm of x square for all x belong to Rn, where this norm denotes the equilibrium norm. Okay, and by definition of equilibrium norm we can say that a norm of x square, if this norm is equilibrium norm, can be written as x transpose x. Okay, this is by the definition of equilibrium norm. We need to find out whether the following statements is or are always correct. A must be orthogonal. A is equal to I, where I denotes the identity matrix, the only solution. The eigenvalue of A are either plus or minus 1 and A has full rank. Okay. So let's move on to the solution. We have given matrix A, which is an n cross n matrix, and we have norm of Ax square is equal to norm of x square for all x belong to Rn. Okay, and we know that, and this norm is equilibrium norm. So equilibrium norm can be written as this norm of x square can be written as x transpose x. Okay, by definition of equilibrium norm we can get that norm of x square can be written as x transpose x. Okay, using this property we can write this as ax transpose into ax is equal to x transpose x. Okay, then ax transpose ax is equal to x transpose x, and we know that a into B transpose is equal to B transpose into A transpose. Okay, in this property we get what we get is we get x transpose into A transpose A into x is equal to x transpose x, because AB transpose is equal to B transpose A transpose. Okay, and this we can also written as x transpose x can also be written as x transpose into I into x. Okay, if we compare both sides, then what we get is we get A transpose A is equal to I. We get A transpose A is equal to I. Hence, from this equation, from this equation, what we get is x A must be of this form. A transpose A must be equal to I. Okay, now the first option is A must be always orthogonal. Okay, using the equation, what we get is we get A transpose A must be equal to I, which means A is an orthogonal matrix. Okay, because this is the property of orthogonal matrix. So the matrix A is always orthogonal, which means the statement A is correct. Okay, A must be orthogonal, this is correct. Second is A is equal to I, where I denotes the identity matrix is the only solution. Okay, that we need to find out. So the statement is A is equal to I is the only solution for this set of equation, for this given expression, which is norm of ax square is equal to norm of x square. Okay, so what we get is we have A transpose A must be equal to I. Okay, this we get, which means matrix A must be an orthogonal matrix. Okay, matrix A must be an orthogonal matrix, and any A which is orthogonal will satisfy this condition. Any orthogonal matrix will always satisfy this condition. Okay, let's see A is equal to I satisfy this condition or not. If we take A is equal to I, then I transpose I, this is also equal to I. Okay, so I transpose I will satisfy this condition, but this is the only solution that we will see. Okay, with an example, let A is equal to I belongs to R2. Okay, and A is this matrix 1 0 0 1. This is nothing but I2 in 2 dimension. Okay, let's say this is this column we take as vector x, and if this column we take as vector y, and we plot this x and y, then we get x and y are orthogonal to each other, and the matrix formed by x and y is an orthogonal matrix. Okay, okay, so what if we rotate this x and y by an angle theta, then we get this. If we rotate this x by an angle theta, then it becomes x dash. Y with an angle theta, this become y dash. Okay, and these x dash and y dash are orthogonal to each other. So if we make a matrix A dash, which consists of x dash and y dash as column, then this matrix is also an orthogonal matrix. Why? Because all the columns, these two adjacent vectors are orthogonal to each other. In similar way, we can rotate these two vectors by any degree theta, and we get a new orthogonal matrix. Okay, so multiple number of n number of orthogonal matrices are possible. Okay, which means A is equal to I is not the only solution. Okay, it's not the only solution. There can be any number of orthogonal matrix. Any orthogonal matrix will satisfy this condition. Okay, and one more thing, using Gram Schmidt also we can convert any linearly independent set into orthonormal basis set. Okay, orthonormal basis, which will also give, from this orthonormal we can get orthogonal basis, and if we put this orthogonal vectors into a column of matrix, then this matrix is an orthogonal matrix. Okay, so many number of orthogonal matrix can exist which satisfy this condition. Okay, and this option is incorrect. This is incorrect. Okay, third is the eigenvalues of A are either plus or minus 1. Okay, so let's see, eigenvalues of A are either plus or minus 1 we need to find. So we have norm of ax, equilibrium norm of ax square is equal to equilibrium norm of x square, and we know that we can replace a matrix A with its eigenvalue lambda using this eigenvalue equation in any polynomial of A. Okay, we can replace A with its eigenvalue lambda in any polynomial of A because Ax is equal to lambda x. Okay, if we replace this Ax with lambda x, then we get norm of lambda x square is equal to norm of x square. If we compare both the sides, then we get is absolute value of lambda square is equal to 1, and we get is mod of lambda, absolute value of lambda is equal to 1. Okay, there can be two conditions. If lambda is real number, then lambda can be equal to plus or minus 1. If lambda is complex, then lambda can be equal to e power minus I theta and e power minus I theta. These two conditions can be possible. Okay, so the option is the eigenvalues of A are either plus or minus 1. Okay, it can be plus or minus 1 or it can be complex also. So this option is incorrect. Okay, hence option C is incorrect. Fourth is A has full rank. Okay, so sorry, A has full rank. So option D is A has full rank. So we have A has no non-zero eigenvalue, which means what we get is either eigenvalues lambda is equal to plus or minus 1 or lambda is equal to e power I theta and e power minus I theta. Okay, lambda is not equal to 0 in both of the cases. Hence, since no eigenvalue, no zero eigenvalue A have, which means determinant of A is not equal to 0 and A is full rank. Okay, another way of seeing this is, since A is invertible, why? Because we get A transpose A is equal to I, then A transpose is equal to A inverse. We can write A transpose is equal to A inverse. And since the inverse exists, which means A is invertible, and hence A is full rank matrix. Okay. Now coming to the core concepts that are involved behind the question. So first one is, suppose we have n orthonormal vectors. Let's say v1, v2, vn, which belongs to Rn. Okay, and we form a square matrix. That is, we take these orthonormal vector and put in a column v1, v2, vn. Let's say this is a matrix Q, then Q is also an orthonormal matrix. Okay, because these all columns are orthonormal to each other. Okay, then Q is also an orthonormal matrix. The same is true for orthogonal, which means if v1, v2, vn, these vectors are orthonormal to each other. Okay, these are orthonormal vectors, and if we met a matrix Q, then this Q is an if these are orthogonal vectors, then this Q will be an orthogonal matrix. Okay, now second one is, matrix A is orthogonal if and only if A transpose A is equal to I, or we can say that A transpose is equal to A inverse. Okay, A must satisfy this property for A to be orthogonal. And there are some properties of orthogonal matrix, which are, first is determinant of orthogonal matrix is equal to plus or minus 1. Second is, any orthogonal matrix preserves norm length, which means if we take any vector, let's say x belong to Rn, and multiply this vector with A is an orthogonal matrix. Okay, then the norm of x is preserved. Okay, this which means that norm of this new vector is equal to norm of x. Okay, that is, if we take a vector A, multiply with matrix A, which A where A is an orthogonal matrix. A is an orthogonal matrix, and if we take norm, then this is equal to the norm of X. Okay, what does that significant? What's its significance is, which means A does not change the length. Okay, multiplying with A, which is an orthogonal matrix, does not change the length. It is just a deflection, okay, or rotation. We can see this matrix as a reflection rotation. It is rotating the A, rotating vector A. It is creating a reflection of A, and not changing the length of the vector. Okay, C is all eigenvalues satisfy mod of lambda is equal to 1, and it must be of full rank. Okay, these are the characteristics of orthogonal matrix. Orthogonal matrix. Now coming to the few practice problems, which are, first one is, let A, which is an n cross n matrix, the norm of A is defined as norm of A square, which is an Euclidean norm, is equal to max of x not equal to 0, norm of Ax square, which is an Euclidean norm, divided by norm of x square, which is, this is also an Euclidean norm. We need to find which of the following statements are always true. First one is, norm of A square, which is an Euclidean norm, is equal to lambda max of A. Norm of A, which is an Euclidean norm, is equal to sigma max of A. Norm of A square, which is Euclidean norm, is equal to lambda max of A transpose A. And norm of A, which is an Euclidean norm, is equal to sigma max of A transpose A. Where sigma max is largest singular value of A, okay, and lambda max is largest eigenvalue. Okay, sigma max is largest singular value of A here, and sigma max of A transpose A, largest singular value of A transpose A, like this. So there is one hint. Let's say how do we proceed that question. Here we have norm of A square, this is an Euclidean norm, is equal to max x not equal to 0. This, if we open this term can be written as x transpose A x by x transpose x. Okay, this term can be written as this. Okay. So if we know that we can replace any matrix with its eigenvalue, in the polynomial of A. Okay, so if we replace A transpose A with its eigenvalue, let's say lambda of A transpose A. Okay, if we replace A with the eigenvalue, and then solve this equation, we get that option B and C is correct. Okay. Now second one is, suppose a matrix A which belong to R, which is an n cross n matrix, satisfy the property which is norm of Ax, which is an Euclidean norm, is equal to C into norm of x. This is also Euclidean norm for some constant C greater than 0, and for all x which belongs to Rn. We need to find which of the following statements are always true. First is, A is orthogonal, A has singular values all equal to C, A transpose A is equal to C square I, and all eigenvalues of A have magnitude C. Okay, so how do we proceed to that question? Yeah, we have this term. Okay, we have to, if we take square of both the sides, okay, if we take a square of both the sides, x square can be written as c square x square. Okay, if we open this term, then this can be written as this, and right side can be written as this. If we compare both sides, then we get A transpose A minus C square I is equal to 0. Then A transpose A is equal to C square I. Okay, if we solve this equation, then we get the option B, C and D are correct. Okay, thank you. If you have any doubts or queries, let me know in the comment section below. You can also join our Telegram channel for the discussion or to ask any doubts directly. And for more such content, don't forget to subscribe. Thank you.